Today we're gonna explain you burst balloons. This is a hard problem in Leetcode. I think the most hardest part of this problem is trying to understand how to model this problem into a DP problem. Pretty hard to come up with. So, okay, without wasting any further time, let us first go through the problem statement and understand what it is wanting us to compute. So here goes the problem statement. You are given n balloons indexed from 0 to n minus 1, and each balloon is painted with a number on it represented by an array nums. You are asked to burst all the balloons. If you burst ith balloon, you will get nums I minus 1 into nums I into nums I plus 1 coins. If I minus 1 and I plus 1 goes out of bounds of the array, then treat it as if there is a balloon with 1 painted on it. Return the maximum coins you can collect by bursting the balloons wisely. Okay, so I'll try to explain this problem statement. I just read it, but I think it is very hard to understand, so I'll explain it. So they have already given an example of explaining, which helps explain what this problem statement is. I'll take the same example. Hopefully, I can finish it quickly. Okay, so 3, 1, and 5, 8, right? 5, 8. So ideally, so what the question wants us to do is wants us to burst all these balloons, but bursting each balloon will give you some points using some simple logic, and then once you are your objective is to burst the balloons in such a way that you get the maximum, you can collect the maximum points, right? So for example, I'll not here I'll not try to do the optimal way. I'll just try to do what is the, I mean, logic, and how do we collect points. Then we'll come to what is the optimal way of solving it, and how basically we'll model it into a DP solution and so on. But first, let me just explain the problem for you. So suppose we decide to burst this 3, right? What they're telling is, since 3 is an element which is at the edge, right? And then there is nothing here. So the way to compute this is you take the way to compute number of points you get by bursting this balloon is you take this particular the value at this particular index, which is 3, multiply it by the value which is on the index right to it, which is 1, and also multiply it by a value uh, to the index left to it. Now the problem here is there is no index, there is no value at the left of it, because it is the leftmost index itself. So in those cases, the problem wants us to consider one has been present here. So just consider that virtually one is existing here, and then we take this number and then we multiply by one, and then we get the number of points that we get by collecting this balloon, right? So we get 3 points here. Pardon my handwriting, I'll rewrite this. 3 here, and then okay, then after this, what is left behind? So we get 3 points, and then we have 1, 5, and 8 left behind. Suppose we again decide to burst this, right? And then in this case, we get 1 into 5 for this, and then nothing is here, so we'll take 1 into 5 into 1. This is exactly what we get, right? So this is the way we keep on collecting the points, and then ultimately we'll burst all the balloons and we'll collect a set of points. But the I think the way that I showed here is not the optimal way, but we need to figure out what is the optimal way to burst the balloons so that we can get the maximum amount of points. Now that the description of the problem is very clear to us, let us try to see how we will approach this problem, right? So the most important thought of the video is here. So in order to solve this problem, I'll give you this scenario. So this is an array, right? We have a left sub array and we have a middle element, right? So here I'm just trying to divide the problem into a smaller sub problem, and that is how obviously we have to model the DP solution okay. So this is the main thought. So we have this kind of this element which is sandwiched in between these two ranges, and what we say is that we will burst this middle element at the end, right? We'll burst this middle element at the end. What that will do is that this will make this sub problem, which is what is the maximum value that we can get uh, by bursting elements of this right subarray, right? Right subarray. Let me denote this as R, and then we have this left subarray. Let me denote this as L. So by bursting the elements of R subarray, uh, what is the maximum value we can get? If we have already said that we are going to burst this current element at the end. So we're gonna burst elements of R in any order and elements of L in any order, and then we are gonna burst current. That means that this entire algorithm, which tries to compute the number of elements and the maximum number of points that we can collect by bursting elements are in an optimal order, is totally independent of what is happening in the left subarray and what are we bursting here in the left subarray, right? Because we already decided the current is the element which is the last to be burst. So no matter what order we burst elements in the left subarray, uh, it will not affect our computation of the right subarray. For example, suppose we are going to burst, we are going to decide that this is the first element that we're going to burst. The leftmost element of the right subarray is the first element that you're going to burst, right? In that case, we know that the left element of this will always be current, and we don't need to know anything about the elements of the left subarray, right? What element is left after some sequence of bursting that we, or whatever gets bursted in the left subarray, or what is the order of bursting in the left subarray, or any information about the left subarray whatsoever, we don't require to know, because we already know that current will be the last element which will be bursted. So this will always be there. uh, Meanwhile, we are bursting balloons in the right subarray, right? So in this way, we are able to bifurcate this problem, or divide partition this problem into smaller sub problems. So if you want to find the solution of what is the optimal solution of bursting, optimum order of bursting in a particular subarray, what we need to do is that we obviously will keep keeping we'll obviously keep everything else as constant, right, here on the left and right. And then what we only need to figure out, and then we'll basically fix a particular element inside this subarray, right, inside this subarray range, which is bounded by L and R indexes. And then we'll figure out what is the maximum what number of coins that we obtain, and we'll be moving this element to other positions, right? We'll be moving this element throughout. So basically, we'll move this mid element, which will be basically divide the left and the right sub problem, or subarrays in this case. We'll be moving this mid element, or this sandwiched element, from the left index to the right index. And that's how. And then for every position of the this middle, let me note this by M. For every position of this M element, we'll calculate what is the maximum number of coins that we can get. And then whatever position of M is the most optimal, which will corresponding to the maximum number of points that we collect, will be our answer, right? So that is the approach that we're going to take for this, right? So let's go to the code and try to explain what is happening here. So so now, okay, so what we do is that, okay, for the sake of convenience, once we have this nums as input, on which we have to basically compute our result, we basically note down the size of the nums in a particular kind of variable called n for easier computation. And then why we do dp n plus 2 plus 2, uh, because we will be referring to, uh, I think we will be referring to db current plus 1 plus, right? But I don't think we need this, right? So let me see. I don't really think we would need this current plus, right? I think if you keep dp of n length plus 1, length less than n length plus 1, left minus 1, dp n 1, let us keep it n plus 2, because we are gonna append the numbers 1 to the front and back of the array, because obviously uh, we need to, like, we have this computation, which is good. I'll get to the what is computation means later. So again, but we have this computation, right? So for this, if left is at 1, it will try to access 0, right? It basically we'll try to access an element which is on the left bounds of the subarray. So what we have done is that we have already populated an element on the left bounds of the subarray. And then we basically the subarray existed between indexes 0 and n minus 1. Now we have populated an element to the left of 0 by this step, right? So that means this particular access would never go out of bounds, and will never give a runtime memory. And for similarly, for the right access, right plus 1, when index is at the last index, right? That is n minus 1. We have already pushed a value to the right of it. So that means this also would never give any runtime issue. So that is why this is being done. And now since the elements of the subarray have increased to n plus 2 because of the insertion of these two elements instead of n, we basically kind of populate our dp. Yeah, basically we make a dp matrix of dimensions n plus 2 into n plus 2 cross n plus 2 instead of n cross n, right? Once it is being done, and then uh, uh, s- uh, and then let's move forward what is happening. And next we basically populated everything by 0, because obviously if something is not possible, then the value would be 0. That's why we have done that. And then we basically go through the entire length. So what we're doing is, so here we are, what we are doing is we are basically having a subarray, right? So let me go back to the figure. So at a particular instant, what we're having to do is we basically are calculating, we're basically choosing a kind of a sandwich element which will be bursted at the end, and then we have a right and left subarray, which whose value we need to know when this is being computed, because that is how dp works, right? So that means that for calculating this particular range, we need it will be beneficial for us if we know all the smaller ranges whose length are less than this range. So suppose this length is L, so we need to know this range also, right? Because we need to know L minus 1 also, because for suppose this element was here, then this entire range would be the right range, and this length would be L minus 1. So we need to know the information about this. Similarly, when the element is instead of here, if the element is here, then also we need to know another subarray which will exist from here to here of length L minus 1, right? That was an iterative node. And for every position, every position this kind of this sandwich element exists in, we need to know the value of subarrays which are having length less than L. So it makes sense for us to compute the subarrays of lesser length starting from 1, and then move to the larger length, so that whenever we are at a particular length, we know that what the values which we require at the for the compute for computations for that particular length, for computing the maximum number of coins for the particular length, then we already have those the computed values corresponding to the smaller subarrays, right? So that we can proceed forward without any issue. That is what is happening here. We are basically we are basically yeah, we're basically moving the length from 1 to n, and then we'll do our computation. I'll come to this in a moment. One thing that I would like to point out is I've looked at other solutions which are existing online, and then there are some other ways of doing this. They're not using this length way, or for some reason, but I think they work, but I was not I was not, it was not easy for me to absorb those kind of solutions. So I have come up with this solution, this similar kind of solution in which you know the answers corresponding to your smaller subproblems before you compute for the larger subproblem by dividing by computing the smaller subproblems first. I mean here the length length, if the lesser length refers to the lesser subproblem. This kind of approach is used for other problems too. I understood. I basically have been using this approach for some time now. So this approach also fits for this problem. So I've used this approach, and this is I find this approach the easiest to understand, at least for myself. Okay, so now that we have let's get back to the let's get back to understanding what this code is doing. So here we are going through the lengths. It is very important that we go from the smaller length to the larger length, and for each length we are basically traversing each range for the length. For example, for length 1, the left would be 1 and the right would be n. Left will be n. Basically, for if you have a if you have a range length of 1, we'll start with left and both left and right pointers here, and then for left one right, and then somewhere in the middle left and right pointers would be here, right? And then at the end left and right pointers should be here. So the last value that the left pointer can reach is n, right? Which is basically which is basically n plus length minus 1. So length is 1 in this case, so that is it will go to n, so which is what should happen. So this is how we calculate. Once we have the left index, then obviously because of the range length, the right index is always fixed. So that is what is happening here. We are trying to move the left index, and then if the left index and the range are fixed, so the right index is automatically fixed by it. And then we are trying to move the a sandwich element or the element which is getting burst last through this range, and then for each position of the sandwich element we are trying to what we're trying to do, we are trying to find out what is the value that we'll get by bursting the last balloon, and then the values of the other sub problem. So I'll explain this recurrence relation. So what is happening is, suppose we have the left pointer here, right? Left pointer here and right pointer here, and we have this sandwich element called cur somewhere in middle, right? And then what we're trying to do is we know this L minus one and R plus one, right? Even if R is at the last element, we know that this exists because we have already populated, we have already appended one to the end on the right end, right? As I explained earlier. So what will happen? All these balloons will be burst, and this will be burst at the end. And then if when this is balloon is burst, that means its left element would be this index, and I would be residing at this index, and the right element would be residing at this index. So basically, the number of coins that we get by bursting this would be nums of cur, right? Nums of cur into nums of pardon my handwriting here, L minus 1 into nums of L plus 1, right? So that is what we'll get. And obviously this sub problem, this will be another sub problem which will be defined by dp left index right index. The left index is cur minus 1 here, sorry, pardon me, the right index is cur minus 1 here, and the left index is cur plus 1 here, right? And obviously the right index is R. Again, I would like to apologize for my handwriting, but I hope if you're able to, if you're listening to what I'm saying, so it will be clear what I'm basically writing down. Even though just by looking at what I'm writing down, it will be very difficult to figure out what I'm writing. So, anyways, let me now read this recurrence relations after explaining what it means. So dp left right, we are trying to take the maximum value, right? And then we have we have the number of coins that we get by bursting the last balloon or the sandwich balloon, and then this is the value given from the left sub problem and the right sub problem, which we have already pre-computed, because we make sure that the smaller lengths get computed first, and then obviously we need to return the maximum number of optimal number of or the maximum coins that we can get by bursting balloons in any sequence, starting from the first index to nth index, because it should have been actually 0 and n minus 1, but we have inserted an index to the left, inserted an element to the left one, and inserted an element to the right, so that this reconciliation doesn't cause a runtime error. Okay, so with this, I think I have come to end of explaining my video. Hope you understand this video. Okay, before leaving, one thing that I've not explained is, so when you are trying to compute this smaller lengths, right? Smaller lengths, this thing is constant, right? All of these things are constant. So this smaller length is getting computed, keeping in mind is this right problem is fixed, and this left problem is fixed, right? So that is how it is getting computed. And I have not dug too deep into why this is the case, but this is something that you can think about, that why this still works. This is one of some thoughts. I think these are the kind of thoughts that cause a lot of confusions and prevent you from understanding the complete problem fully. But this is something that you can think about, and this will be a good thought exercise. So with this, I'll stop this video, and I'll see you in the next video. Thank you. Bye.